Hello everyone, my name is Hendrik Waldner and I'll be talking about multi-client inner product functional encryption in the random oracle model. This is joint work with Michel Abdalla, Florian Brouse, Hugo Marival, David Pointcheval and Azam Soleimanian. Starting with some motivation, let's consider we have an encrypted dataset that contains the test and quiz results of Carol and Charlie. Now we want to allow Dave and Aaron to do some weighted sum computation over the test and quiz results of Carol and Charlie, where each of them uses different weights. To guarantee privacy for the data of Carol and Charlie, we need to ensure that Dave and Aaron do not learn more than their desired weighted sums. Additionally, we want to achieve that Alice can provide the test results and Bob the quiz results. With this motivation in mind, let's see what cryptographic primitives we can use to achieve this setting with the desired privacy guarantees. A possible primitive that we could use to achieve this setting is public key encryption. In public key encryption, a setup algorithm outputs a public key and a secret key. The public key can be used by Alice to generate the ciphertext for message X, whilst the secret key can be used by Bob to decrypt the ciphertext and receive the message X. For our use case though, we need fine-grained access control over the encrypted data, whereas here it is only possible to output the complete message X or nothing in the decryption procedure. To allow for this fine-grained access control over encrypted data, the concept of functional encryption was proposed by Bonnet, Sahai and Waters in 2011. In functional encryption, the setup algorithm outputs the master public key and the master secret key, where the master public key is used to generate encryptions, as in the case of public key encryption, but the master secret key is used together with the function f to compute a functional key. When this functional key is used for the decryption of a ciphertext, the output is the function associated with the functional key applied on the underlying message X of the ciphertext. This primitive gives us the desired fine-grained access control that we need, but it only allows us to compute functions that take a single input value. We need a notion that allows for the computation of functions that take several inputs. A primitive that does exactly this is multi-input functional encryption, which is a generalization of functional encryption. In multi-input functional encryption, we have the same setting as in functional encryption, except that the decryption procedure takes several ciphertexts as an input instead of just one. This means that both Alice and Carol can use the master public key to generate encryptions of their inputs x1 and x2. One problem with this primitive is that we have some information leakage through mix and match attacks. For example, if Bob is in possession of a functional key for the function f and he receives the encryptions of x1 and x2 from Alice and Carol, he's not only able to compute f of x1 x2, but also f of x2 x1. Additionally, if Alice provides another encryption of an additional message x1', Bob can again compute all the combinations with previously encrypted messages. To prevent this information leakage, we turn to the more restrictive notion of multi-client functional encryption. In this setting, each input position is associated with its own secret key, and ciphertexts are generated using specific encryption labels. So in this setting, Alice uses her key to generate an encryption of x1 under the label L1, and Carol uses her key to generate an encryption of x2 under the label L2. In this case, functional decryption only works for Bob if the labels of the ciphertexts he wants to decrypt are equal. So here this would be L1 equal to L2. Therefore, the two mix and match attacks that we described before are prevented, since the inputs of Alice and Carol cannot be switched as they are generated using different encryption keys, and Alice and Carol can use different labels to prevent mix and match with previously encrypted messages. It has been shown that it is quite difficult to construct multi-client functional encryption from standard assumptions for a general class of functions. To nevertheless allow for practical constructions of multi-client functional encryption, we focus on more specific function classes. In this work, we consider the inner product functionality, which has first been considered by Abdalla et al. In 2015 for the single input case. For an inner product multi-client functional encryption scheme, the functional decryption keys are associated with the vector y, and then the decryption procedure simply outputs the inner product of x1 concatenated with x2 and y. The first time that multi-client functional encryption for the inner product functionality was constructed was by Chotard et al. In 2017. In this work, the authors present a scheme in the random oracle model based on the DDH assumption that takes scalars as an input in every position. In a follow-up work in 2018, they show how to generalize this in a black box way such that in each position a vector can be encrypted. In 2019, two works were published in this area. The first work by Abdalla et al., where the authors presented a black box compiler that shows how to turn a single input functional encryption scheme into a multi-client functional encryption scheme in the standard model. And since the underlying single input functional encryption scheme can be instantiated using MDDH, DCR, or LWE, these are the assumptions that they rely on for their compiler. Concurrently, in the work of Libert and Titou, the authors show how to construct a multi-client functional encryption scheme directly from the LWE assumption, also in the standard model. In this work, we show how to construct multi-client functional encryption for the inner product functionality directly from the MDDH, DCR, and LWE assumption in the random oracle model. Our MDDH-based construction can be seen as a generalization of the construction of Chotard et al. From 2017, handling vectors as an input. The DCR-based and LWE-based constructions are only able to handle scalars as an input. However, using the results of Chotard et al. From 2018, we can generalize this to vectors. Now you may ask why we rely on the random oracle model if we already know how to realize multi-client functional encryption in the standard model. And the answer is quite simple: we want to achieve better efficiency and higher practicality. Therefore, in our paper, we also present implementational results of our constructions based on the different assumptions. Before describing how our constructions work specifically, we give a generic overview about how to construct multi-client functional encryption in the random oracle model. After introducing the different complexity assumptions we rely on, we will present our constructions more specifically. The setup algorithm in our multi-client functional encryption scheme generates n different secret keys for all the parties and sets the master secret key as the union of all the different secret keys. Finally, the setup algorithm outputs the secret key SKI to party PI and the master secret key to the party that generates the functional keys. To generate an encryption of the message XI under label L, we first query the random oracle on the label L, and then use the random oracle output UL together with the secret key SKI to derive a label key. The function that is used to derive this label key depends on the hardness assumption, and we will specify later how this function f actually works. For the last step of the encryption, the label key is used together with the message XI to generate the ciphertext. To generate a functional key for vector y, where y can be seen as the concatenation of y1 up to yn, we simply compute the sum of the inner products of SKI with yi, and this gives us our functional key SKY. The functional key is basically a leakage of the master secret key that depends on the vector that is used in the key generation procedure. Now that we have finished the generic overview, we are ready to introduce the underlying complexity assumptions. The first complexity assumption that we need is the MDDH assumption. The MDDH assumption says that if we have a matrix A with k plus 1 rows and k columns, and we multiply this matrix with a random vector S of dimension k, then the resulting vector in the exponent of a generator G is indistinguishable from a random vector of dimension k plus 1 in the exponent of the same generator. The bracket notation here denotes the fact that the matrix or the vector are in the exponent of the generator G. Since the matrix A has k plus 1 rows and k columns, it follows that there exists an additional vector B such that B transposed multiplied with A is equal to the 0 vector, and therefore A together with B form a basis. We need this later in the security proof. The second hardness assumption that we rely on is the DCR assumption, which says that a random element from the multiplicative group modulo n square is indistinguishable from a random element to the power of n modulo n square. Also here we have an additional property, which for this assumption is the bijection epsilon from z modulo n times the multiplicative group modulo n to the multiplicative group modulo n square, which takes as an input two values a and b and maps them to 1 plus n to the power of a times b to the power of n. The last assumption that we use for our construction is a generalization of the decisional learning with errors assumption, which says that the product of the matrix S with m0 rows and n0 columns, where m0 and n0 are some LWE parameters, multiplied with the vector a of dimension n0 plus some noise is indistinguishable from a random vector t of dimension m0. Besides the LWE assumption, we also need to introduce the rounding operation from ZQ to ZQ0. This map takes as an input an element from ZQ and maps it into the smaller space ZQ0 by multiplying it with Q0 divided by Q and then applying the rounding operation over the integers. Now we can use the introduced complexity assumptions to specifically describe our constructions. Let's begin with the setup algorithm. The secret key in our MDDH-based construction is a matrix Si with k plus 1 rows and k columns. For the DCR-based construction, the secret key is a single element Si, and for the LWE-based scheme, the secret key is a vector Zi. To encrypt the message xi under label L, we first query the random oracle on the label L to receive the value UL. In the next step, we can generate our label key. For the MDDH-based construction, the label key is the product of the matrix Si and the vector UL. For the DCR-based scheme, the label key is the random oracle output to the power of Si, and in our LWE-based construction, the label key is the inner product between the secret vector Zi and the random oracle output UL. To encrypt the message xi in our MDDH-based scheme, we simply add the label key to the message xi and raise it to the exponent of a generator g. When we compute the decryption of the ciphertext using a functional key, we receive the inner product of x and y also in the exponent of g. Therefore, in the last step of the decryption procedure, a discrete logarithm computation is necessary. For the DCR-based construction, we need to multiply the label key together with 1 plus n to the power of the message xi, and in our LWE-based construction, we proceed similarly to the MDDH-based case, with the only difference that instead of raising g to the sum of the label key and the message xi, we apply the rounding operation on the sum of the label key and the message xi. Before we can analyze the security of our schemes, we need to specify the security goal we want to achieve. We do this using an indistinguishability-based security game where the adversary has access to 3 different oracles. The first oracle that the adversary has access to is the encryption oracle. The adversary can query the encryption oracle for every position I and label L using 2 different messages x0 and x1. It receives as a reply an encryption using the secret key ski of the message xb under the label L. The challenge for the adversary is to guess the bit b by outputting a bit b prime. If this bit b prime is equal to b, then we say that the adversary wins the security game. We say that a scheme is secure if the probability that the output bit b prime is equal to b is around 1/2 for all possible adversaries. In addition to the encryption oracle, the adversary also has access to a key generation oracle where it can submit a function f for which it receives as a reply the corresponding functional key. To make sure that the adversary cannot win the security game trivially, we need to enforce that for every functional query that the adversary asks, the function applied on the left challenges over all the positions must be equal to the function applied on the right challenges over all the positions. The adversary also has access to a corruption oracle where it can submit a position I and receives as a reply the secret key of the corresponding party. The adversary is only allowed to corrupt the party PI if all the encryption queries it has asked for this party contain the same challenge messages. This means that x0 needs to be equal to x1 for all encryption queries asked for I. If this is not the case, the adversary can also trivially determine the bit B and win the game. After introducing the security game, we can now give an overview of the security proof of our constructions. The proof of security proceeds via a hybrid argument with different games. For the transition between the different games, we rely on the programmability of the random oracle and the different complexity assumptions. In our security proof, we only consider a specific label L star. Security for all the other labels follows by a hybrid argument over all the labels. The goal of our security proof is to change the distribution of the master secret key in such a way that together with a programmed random oracle, we can hide the challenge messages under the label L star. Our security proof starts with the game G0, where the encryption oracle always replies with an encryption of the left challenge message x0 for every party I, and the random oracle is instantiated using the hash function h. In the first transition, we replace the hash function with a truly random function rf. This transition is justified by the random oracle model. In the transition from G1 to G2, we replace the random values that are output by the random function with values from the underlying assumptions that are indistinguishable from random values. In the case of the MDDH-based construction, this is the matrix A multiplied with a random vector R. For the DCR assumption, this is a random value to the power of n modulo n square, and in the case of the LWE assumption, this is an LWE tuple where we have the matrix S multiplied with the vector A plus some noise. In the next transition, we reprogram the random oracle in such a way that for the challenge label L star, the random oracle outputs a different representation of the underlying assumption. These are the additional properties that we have introduced earlier. For the MDDH-based construction, we let the random oracle output the matrix A multiplied with a random vector plus the vector b times a random scalar. For the DCR-based construction, we apply the bijection epsilon and we consider the output of the random oracle as 1 plus n to the power of a times b to the power of n modulo n square. And for the LWE-based construction, the LWE tuple is extended by adding an additional random vector to the noise term. In addition to this, between the transition from game G2 to game G3, we need to use some noise flooding techniques and apply the rounding operation to a smaller space. This is necessary to handle the information leakage through the encryption queries in the LWE-based construction. After the transition to game G3, the master secret key has the desired distribution such that it can hide the challenge messages under the label L star. This allows us to change the encryption oracle from encryptions of x0 under the label L star to encryptions of x1 under the label L star for all parties PI. To complete the security proof of our constructions, we need to consider the backward counterparts of G0 to G3, which are the games G5 to G8. This completes the security proof. Thank you for your attention. We look forward to answering any questions you may have.